I am Fraser Kane, publisher of Universe Today. And this week, back with our regular co-hosts, we've got, actually most of our regular co-hosts, we've got Morgan Renberg. Morgan.
Hey Fraser, happy Wednesday.
Happy Wednesday to you as well. I give myself like man, my screen is a little off. I give myself like better part of a month. I get like 4 more of these where I get forget the date wrong, and then you guys can think I'm like literally losing it. We've got Paul Matt Sutter.
It's always Wednesday where I live.
Oh, and of course I've got to say doctor. I'm assuming all the guests are doctors too. Once again, Fraser and many doctors. So we got a special live guest. We did a recorded guest last week. This week we're going to have live guests. So let's get on with the special guest. Joining us from the future and Australia. Oh, there's 2 of you too. Okay, we got to figure out how we're going to do this. So we've got, and I'm not sure which one's going to come up first. Let's see what happens. We've got Anais, Möller, and Brad Tucker. Anais and... There, we got Brad first.
How's it going?
Welcome to the Weekly Space Hangout.
Thank you, and it's not quite Friday, and it's definitely... Wednesday was so yesterday.
And let's see if we can get... Anais, can we get you to come onto the screen here? Let's see.
Let's say... hello, everybody, for me, it's Thursday. It's 10 a.m. in the morning, so it's a good time. Before it was going to be like 3 a.m. in the morning if you had the usual scheduling. But very happy to be at 10 a.m.
That's right. The timing works out well depending on where you live in the world. So for some people, it's gotten better, and for other people, it's gotten worse. And I know our Europeans are not super pleased. So let's start. Since you're on the screen right now, Anais, why don't you tell us who you are and what you do?
So I'm a postdoc here at the ANU, and I'm co-leading with Brad SkyMapper Transient Survey. So basically, we're searching the sky for transients, and part of that is searching for supernova. So we're trying very hard to find them, to do cosmology, hopefully, with them.
Now, when you talk about transients, you're talking about things that are changing in the night sky. So not... Because I mean, I know we actually had folks from the LSST, the Large Synoptic Survey Telescope, and that was, that is just going to be this whole time-based transient astronomy. It's a whole nother world. So is that sort of that? Is that right?
Yes. So what we're searching is things that change in the sky. You have a bunch of different astrophysical objects that do so, and we're searching in the optical. So there is from variable stars to supernova. We're specifically interested in what we call cataclysmic things, which basically is the explosion of the star and then it's gone. So you have novas and supernovas. So novas won't be of our interest because they are not killing the star, and we cannot do cosmology with them. But we're interested in supernova mostly, and some other things.
And so, Brad, as a person who loves to watch things explode, supernovas are awesome. Supernovae are awesome. Why specifically, though, are scientists looking for supernovae? What's it telling us?
Well, besides just enjoying, just knowing that an entire solar system exploded before your eyes kind of makes you feel powerful. But really what we're trying to do is use these to measure fundamental properties of the universe. You can measure things that, how the universe is formed, how the universe is growing, what is causing the universe to grow, and we call this dark energy. And when we say that you're all made of star stuff, right? Well, you're all made of dead stars. And that stuff had to come from somewhere. So you get to see the elements formed in real time, in addition to understanding how stars live their lives and measuring the biggest discovery kind of in the past 20 years, besides, related to even gravitational waves, and that is, what is this dark energy that is dominating the universe and will cause our universe to end?
And the discoveries of supernova at this point are largely done with a lot of amateur help, right?
Yeah, it links in together, and this is the whole point of doing a citizen science project. Is some of the best studied supernova we've ever had have been from amateurs. We had a conference a couple of years ago. Every supernova person was there, and the most famous person everyone wanted to meet wasn't Brian Schmidt, who won a Nobel Prize. It was Father Bob, who was an amateur astronomer from Australia, who discovered all of the important supernova we care about. Because the nearby ones are the ones that tell us the most and allow us to do the best measurements, which help us with the further away ones.
And right now, how many supernovae tend to get found every year?
Ooh, that's a good question. What are we up to, Anais, in terms of lettering? So supernova are lettered, the first one's A and then through Z, and then we go AA through Z. What are we at, Anais?
Right now we are in R, but that's transients, not supernova.
True. We're
so
talking
it depends on the SkyMapper is discovering around 40 type 1A supernova per year, hopefully.
But yeah, in general, we're in we're getting close to the thousands.
Yes. So it depends how far away do you see. So we are actually close by. There are other experiments that will look far deeper, like the Dark Energy Survey, which we belong also to. And it's a different game. Here we're trying to cover the whole sky, so we can get a lot of supernova that are close by. And in Dark Energy Survey, we look very far away and a little window.
Right, and so let's talk about about this citizen science project that you're working on. How are you bringing sort of regular folk in to be able to help you search for supernovae?
Well, finding supernova, it's easy, the theory. The truth is a little bit harder. So basically you have a new image, let's say from yesterday, and you compare it with an old one. And if there is a supernova, you probably will see a blob shining up there that wasn't there a year ago. So we do that with the computer. We actually do some machine learning to try to reduce the number of possible supernova. But there's still a lot to improve. So we have to look with our eyes. The humans are amazing. So we have our heads are much better than the computer, and we can detect if that's a possible supernova or not. So we were doing that by eye, and now we are doing it through the Citizen Science Project, where everybody can help us find them. So basically you see these three images, the new one, the old one, and the difference between them. And you can help us to determine if that's a transient, a real transient or not. So that's the whole idea about the program. And that gets re-injected to us, the information, of course.
So can you kind of clarify that terminology between a transient and a supernova? What are you talking about there?
Oh, transient is anything that changes in the sky. So we may find also variable stars, like our LIRA. We have found many of them, actually. So things that change in the sky will be transients, something that varies with time and fades away, probably. And supernova are part of transients, but transients are not all supernova.
Right.
And you can get planet transients, right? It's anything that changes. And this is the cool thing about the Citizen Science Project, I think, is that everyone did spot the difference when they're a child. Well, now you actually can do it and make discoveries about the universe. So combining something that's just fun with something that is even more fun. I'll let you decide which is more fun and which is just fun.
Now you were saying that you've got this interface. You're doing this through Zooniverse, right? And you've got this interface that allows people to compare. So, like, what are they looking for? They're looking at three images. I guess the computer has already detected what it thinks is some kind of transient, and then they have to sort of really nail it down. How does this work?
Yes, basically it's just observing. The computers are sometimes very dumb and they don't see the difference between an artifact from like a bright star from a real transient. So you basically see, the important thing is that the difference image, you usually have a single blob there in the center of the image, which will be the difference between the new one and the old one. And you should have a blob, a circular-like thing that has changed between them. The computer kind of knows that, but we are much better. Like humans, we are incredible about this.
Yeah, it's like, you can teach a child to do as good of sort of research into. I know back with the galaxies, you're trying to figure out the direction that the galaxies were rotating. You could teach a 4-year-old to detect whether it was a spiral galaxy or some kind of elliptical galaxy, and even which direction the galaxy arms were rotating, and use that to figure out the distribution of galaxies across the universe. And same thing with what's happening with CosmoQuest. You've got craters, and you can sort of see how those craters go. So it's kind of amazing. It's that there still is a great need for human beings to get in there and actually participate in the science. How long have you been running this operation for now?
We launched it on May this year. And something that we haven't mentioned is that we report when we find a transient to the transient name server, which is an International Astronomical Union page, and it gets a name. We cannot name a supernova because it's a dying star, but we put in the discoverers, the first 3 volunteers that actually tag that object. So you get some recognitions for the work that you have been doing.
Like actually in the paper later on?
So we haven't... Go ahead, Brad.
Yeah, I was gonna say, well, it's essentially the official recognition by the International Astronomical Union. They're part, and I think this is the cool thing, and why it's important is not only are they helping us, they are part of people are part of the discovery process along with us. And eventually, when we write our cool papers that we're working on, we're going to invite them, as much as possible into this space. They are citizen scientists.
Exactly.
Yeah, absolutely. So what is your hope? What are some of the big kind of unsolved mysteries that you're looking for in your research into supernovae? What would you like to know?
Ooh, how long do we have?
About 3 minutes.
One of the biggest questions is we use these specific type, these thermonuclear events. So these are the giant white dwarfs that explode. And we don't understand exactly how they blow up. And, the way we use supernova is if you know how bright something is and how bright it should be, you can calculate the difference in brightness and get a distance. But if you don't know how bright, if you know how bright the bulb is, it works. But if you don't really know what kind of bulb you have, then your measurements are a little bit off. And these are one of the biggest things that we're trying to address, and how to use that bulb better. And we need to find these things earlier and quicker so we can get as much data as possible. And that's where the people are literally helping us. We would have to spend hours, each person on the team, every day doing our science, all the processing, analysis, database stuff, in addition to finding them. So by allowing these people to help us find them, a key part of this, we can be more efficient and quicker and start to answer these questions.
I mean, I think, if I understand, the type 1a supernovae, right? Those are the ones that are this material accreting onto this white dwarf, and then the white dwarf explodes, and that gives you that standard candle to be able to know how far away those things were. But, I mean, is there a way potentially to use other kinds of supernovae as standard candles as well, if you learn more about them and what you sort of see in the detonation?
So people have tried. There is a huge effort to do that. But the advantages of type 1a is that they're easy to standardize. And the other ones, you need a lot of parameters, and there is a lot of uncertainty there. But also type 1a's are very bright. So if you compare it to like a type 2 supernova, we can see them, like type 1a are much brighter. So we can see them further away. And that's a huge advantage because we couldn't probe the acceleration of the expansion of the universe with a supernova that were only close by. We need to go very far away.
So I've got a couple of questions from the audience right now, and I like this one here. This one comes from War Basher, which is, if you're developing are you developing some ways to predict and time supernova? What about Betelgeuse? And I think that's a question that's on all of our mind. When will Betelgeuse explode already?
Explode! I really want it.
Yeah.
It's going to be great. I'm really waiting for this. I hope I'm alive for another 20,000 years. But these are the sorts of things like Betelgeuse, and we did this with the supernova 1987A. So this occurred in the Large Magellanic Cloud. By being so close with some of these, we can measure them beyond just our normal telescope colors, our normal optical colors. We can see particles, neutrinos, and now in the era of gravitational waves, if Betelgeuse blows up, we'll detect the wave of gravity going through space and being able to probe the light time versus the gravity time and really actually measure independently these things. So I hope that it blows up any day now, because it would be cool, and it would allow us to just see things that we never did, and that's what 87A in the Magellanic Cloud did. So go Betelgeuse!
I mean, we apologize for the terrible disaster that will befall anyone who's near
we'll have a moment of silence for the Betelgeuse system. Yeah.
But we will gaze on it in wonder in the middle of the day, which is great. We've earned it.
Exactly.
Yeah.
We're due.
We usually don't see things that change in the sky, like stars changing with the naked eye, but we will be able to do that with a Betelgeuse. So that's something mind-blowing.
Now, Brad, before we started the show, you actually mentioned to me some kind of exciting uses for the Kepler Space Telescope that I wasn't aware of.
I mean, a lot of people are aware that, two of the wheels that helped Kepler point broke, and so there was this new mission called K2, and so it kind of rotates now between looking at planets and then galaxies. And we've actually been using SkyMapper to work with Kepler and discover supernova. And so with Kepler, you can actually see within minutes the explosion. And so the end of K2, so it's about to run out. Dedicated to actually finding exploding stars. So SkyMapper will be looking at the same exact patch of sky Kepler is, and we're going to see in detail, the subtle things that happen with SkyMapper and supernova that we can't see normally because we only observe it once a day, but we'll be seeing it every 30 minutes. And so citizen scientists can look in the SkyMapper database and find exploding stars that are helping Kepler. And so it's a really cool connection of a bunch of great facilities all around the world and above us.
Fantastic. It's nice to see them using every last little bit of the capability of Kepler as it runs out of reaction wheels. So I'm
exactly. It's they're going to run it into the ground. Essentially. If they could crash it into Spitzer, they probably would. But no. It's going to go to the great craft. In the sky.
Yeah. Well, so where do people go to get involved?
In the Supernova sighting project.
And find out more. Yes. Now's your chance to self-promote a thing you're working on. Feel free to provide your Twitter handle if you like. That too. But
yes, sure. So you can go in the Zooniverse page. It's called Supernova Sighting, the project. I'll post the link in the chat in a second. But you can go in and there is an About page. You can see more. There is a link to our webpage of the SkyMapper Transient Survey. If you want to learn more about the science that we're doing, we're usually around with the talk section, so you can ask us questions. So it's pretty interactive. So feel free to come in and
that sounds great.
Take a look.
And if you want to ask us, you can bug us on Twitter on btucker22. You can also do at SkyMapper and Anais. What's your handle? At
Anais_Möller.
Perfect.
I don't think I can post that in the YouTube actually channel.
Yeah, you should be able to. Yep. Awesome. Well, Brad and Anais, thank you so much for joining us on the Weekly Space Hangout, and good luck with your continued supernova observations. I look forward to your findings.
Yeah,
well,
thank
we
you
look
for
forward to
having us.
sharing. We look forward to sharing Betelgeuse blowing up with you too. So.
Yeah. But if you find out it's exploding, please let me know.
Oh, we'll have another hangout. We can watch it together on the Weekly Space Hangout.
That sounds great. All right. Thanks a lot, guys.
Thanks.
Bye. Have a great day.
All right. Paul and Morgan, let's get on with the news. I am going to randomly choose. Morgan's on my screen right now. Morgan, you get to go first. Let's talk about ice near Mercury.
Yeah, this is a great story to build off of what we talked about last week with the end of Cassini, because we mentioned how Cassini was ending, but the legacy of Cassini in terms of the data it collected will live on far beyond the end of the actual physical orbiter. And that's absolutely been true with Messenger, which spent a number of years orbiting Mercury earlier this decade before dramatically crashing into the surface of Mercury a couple years ago. And for my money, the most exciting and surprising thing that Messenger discovered at Mercury was evidence of water, specifically water in the form of ice. And this was sort of intuitively a really surprising thing, because we all know Mercury is the closest planet to the sun, and it's hundreds and hundreds of degrees hotter than the Earth, both on its day side and on its night side. And so that'd be the last place you'd expect to find any ice. But it turns out that in the North Pole of Mercury, there are craters that are deep enough that they never see sunlight, that they're permanently shadowed as Mercury rotates around, and they never get hit by light, which carries the heat that would melt away that ice. And Messenger found that in those craters, there were sheets of ice. Wow, that's amazing. But what this new paper showed was that it wasn't just in those few craters that Messenger first looked at. And they went back and looked at those data again with the instrument that Messenger had used to detect the ice. Then they took a different instrument on Messenger, the laser altimeter. And this is a cool instrument because unlike most instruments on a spacecraft that are just taking light in as it hits the spacecraft and making a picture or making a spectrum or whatever, a laser altimeter actually emits light. And this is really important when you're looking for ice in places where there's by definition no light. That ice survives because light is not there. And so it's challenging with all these instruments that collect light to find that ice in the first place. And so they calibrated the laser altimeter on these places that they knew ice existed, and then used it and then went through the data to see if they found other places on Mercury that had similar observations. And they found a couple of really cool things. One thing they found was more craters that had ice in them, again, up in that North Pole area. But what's even cooler than that is they found places sort of at surface level that seemed to have large sheets of ice that would span hundreds of or thousands of square kilometers on the surface in areas that were basically in shadow. So they're like the peaks around the craters were casting shadows onto the surface, and sort of tucked in the lee of those places was more ice. And this just sort of reinforces this idea that water in the solar system is everywhere. We never would have imagined it was on Mercury, and yet here it is, but we still don't really know why. We know why it can survive there, but how the heck did it get there in the first place? And that's something that we just don't really understand yet.
Yeah, I was just about to ask that. Where did this sufficient water come from? Because presumably any water that Mercury was born with evaporated away long ago due to its proximity to the sun.
But hasn't something similar been seen on the moon?
Yeah, absolutely. And in both cases, there's basically two hypotheses. One is that comets or asteroids that were full of ice, full of water, crash landed on Mercury's North Pole sometime after it formed. And a lot of that water would have vaporized in that impact, but some of it might have survived and stayed on the surface. That's kind of the more obvious example. In planetary science, if you don't understand why something happened, it's probably because something else hit it. That's the base explanation.
That's awesome.
But there's a cooler explanation, which is that some places in Mercury, there's a lot of hydrogen on the surface. And that could have been, again, delivered by a comet or something like that, or it could have been leaking out of rocks that were in the interior of Mercury. And then since formation, this hydrogen is kind of diffusing out of the inside. And then there's oxygen atoms that are streaming towards Mercury in the solar wind. And maybe some of those sort of bounce off the surface of Mercury, get caught by Mercury's gravity and smash into those hydrogen. And you add hydrogen and oxygen together and you get water. And so this hypothesis suggests that this ice in the shade of Mercury was literally built one molecule at a time over the course of the solar system. And now it's built up to the point where it's hundreds or thousands of square kilometers in size.
And by doing so, does that give us a possible explanation for where, water on Earth came from?
Oh, probably not, because this process would be extremely slow. Most of Earth's water is almost certainly left over from when it first formed. We often, the sort of the popular idea is that comets delivered a lot of water to the Earth. And it's quite possible that comets delivered water to the Earth. And it's even possible that much of the Earth's surface water comes from comets and asteroids. There's data that suggests that might not be true, but it's possible. But the water on the surface of the Earth is actually only a really small part of the amount of water the Earth has. Locked in the Earth's mantle, underneath the crust, is somewhere between 100 and 1,000 times as much water as on the surface of the Earth. And that water has almost surely been there since the formation of the Earth 4.5 billion years ago.
Right, because I had heard that sort of the alternative theory. I mean, there's the comet delivery mechanism, and then there's sort of that the Earth just scooped it up in ice form on the spot over but when it formed. So the Earth, that there was that ice and water ice in the area, and the Earth just scooped it up as it was forming. And so it wasn't that it just got hit by a bunch of comets, it just pulled in that water. But this is like a different mechanism. This is like the sun is blasting hydrogen atoms at Mercury, and because they're hitting a spot that is eternally in shadow, they're not getting kicked out again by the solar wind.
Yeah, we know that the early solar system was full of water because planets like Uranus and Neptune are chock full of it. Planets like Jupiter and Saturn have plenty of water as well. We have the comets, all the icy moons of the outer solar system. And that water probably at the very beginning was spread evenly throughout the solar system. The sun turns on and it suddenly starts baking that away from Mercury and somewhat from Venus. And the Earth manages to form sort of before the water is dispersed from Earth, and Mars probably formed very similarly. And then things start to diverge. And Venus probably had a lot more water early on, but it's close enough to the sun. It had this greenhouse effect. All that water was baked away. Mars lost its water because it lost its atmosphere. It lost its magnetic field. Earth kind of won the lottery from not being too close to the sun, won the lottery for not having whatever happened to Mercury or to Mars that killed off Mars's magnetic field. We just sort of, we're playing roulette, and it all came up right.
And so do you think that is a different mechanism for what happened with the moon? I mean, we know that there are similar deposits in the permanently shadowed craters on the moon, but would that have been perhaps that the moon kept its ice from its formation? Or is that... Because, I mean, the moon is like the place to go looking for helium-3, right? Because there is still material hitting the surface of the moon.
Yeah, probably the moon's ice is not from the formation because the moon formed so violently. Like, even in comparison to how the Earth formed, the moon, we think, formed with a giant collision between the Earth and a Mars-sized object, and that would have vaporized basically all the water that went into forming the moon. So the moon certainly has some water that probably left over, but the water on the surface that came from ice, I would wager, was delivered by comets in the intervening, eons.
So I guess the question is, how do we use this, right? Do we go to colonize Mercury and we live in those permanently shadowed craters and use that water ice to power our dreams and rocket engines?
Sounds great.
I think probably the moon's a better place. It reminds me of, the extended Star Wars universe had all of these just totally weird worlds. And one of them was sort of a Mercury-like world that was very slowly rotating as it orbited its planet. And I'm sure that some nerd out there is going to supply us with the name of this thing. But they built their cities on basically like giant trains. And the train just sort of rolled opposite the motion of the planet around forever. And it, of course, it inevitably broke down, and there's this race against time to fix it before it sort of reappeared on the day side and just kind of ran backwards forever.
I love that idea that you could actually walk faster than the Terminator on Venus, for example. So you could outwalk night or daytime on Venus, the speed that it rotates. So I don't know if it's the same on Mercury.
We're going to need some sort of awesome robot suit to be walking on Venus.
Yeah, no, I mean, not to mention
A small technical detail.
Yeah, not to mention the terrible burning and the frying. Well, that's super cool. All right, so I'm gonna go next. What? Fraser's got a story? It's true, I do. So the
Brave New World.
It is. This is the new format. I can't guarantee that I will always have a story, but let's see what happens. So my story is that a group of Finnish researchers announced today a pretty neat idea for being able to explore asteroids. And so the idea is normally that you send these $100 million, $2 billion spacecraft out to, like Rosetta or to New Horizons and actually do a flyby of one of these asteroids. And so what they propose instead is do a CubeSat fleet of missions. So you could launch them together or you could launch them individually. The satellites would use a system of propulsion called an electric sail. And it's different from a solar sail. So the way a solar sail works is, of course, you've got this big mylar sheet that collects photons from laser beams or the sun, and that allows it to move out into the solar system, change your orbit. So these would deploy this big, long tether, 20 kilometers long, and by having this tether out, it would catch and it would be electrified, and that would then catch the momentum of the protons streaming from the sun, and that would impart 1 millimeter per second squared of thrust. So over, you'd be, 1 second you'd be going a millimeter faster per second, and then, a second later, 1 more millimeter. So it would take a long time. But they calculate that you could then take these spacecraft and you could send them out to the asteroid belt, go past 6 or 7 different asteroids, and then make a return journey using this propulsion system over the course of 3.5 years. They wouldn't be powerful enough to actually transmit from the asteroid belt, so they would have to sort of store all this material on their local memory, and then they would come back to Earth and they would drop off their, they would beam the material once they were back close to home. Each satellite would be about 5 kilograms, so really small, but they would have a 40 millimeter sort of aperture telescope on them, so like the size of a pair of binoculars, like 1/2 of binoculars. And they figure they can do the whole mission for about 60 million euros, which
No.
I'm telling you what they said.
They're wrong.
No,
and no way.
But that you could then get each. So that would allow you to essentially study asteroids at a cost of about a couple of 100,000 euros per asteroid. And
do these 20-kilometer long tethers sit inside the CubeSat initially?
Yeah. So
it's like 95% tether.
It's about half, I think. So the thing will launch. It's actually like a 10-kilogram satellite, and then it reels out this great big long tether, and then uses this tether as a propulsion system. And actually, there was a spacecraft launched by the Finns earlier this year on an Indian mission, on an Indian rocket that was going to be testing out a bunch of technologies, but one of the ideas is this electric sail concept. And one of the sort of the more advanced. Now I definitely get the impression that they're looking for ways to really use, because this is their baby, this electric sail idea. But they proposed other missions as well, like deploying this big, sort of almost a big circle of these tethers out and going out to 100 astronomical units from the sun using just this, using the solar wind in a relatively fast time. Yeah, Morgan, let's get the laughter out of here. Yeah.
What's up?
So I love this idea. I really do. Asteroids are so different. We got to go to a ton of them to really understand anything. We're talking about millions of asteroids out there. There's no way that one at a time, every few years, we're ever going to understand enough about the population of them. Just think about exoplanets. When we were studying 4 exoplanets, we grossly misjudged the true distribution of exoplanets out there and the true variety and uniqueness of all these systems. And the only way we found that out was to have things like Kepler, where we were studying them by the hundreds and the thousands. I love this idea. The notion that you could build 300 of
50.
anything
Only
in space.
50.
Only
50. They'll see 300 asteroids, but they'll only build 50 of these things.
Okay, so
and they
I
don't
retract 2/3 of a
and they don't need to build them all. They figure you can build them and tuck them into the side of existing launch missions, right? So
yeah, I don't know.
Well, it's
to
not
build
like
50 of
packing
anything
it
for
all.
60 million euro that goes into space, to me, is laughably low in price. For 600 million, maybe you could do this, and that would still be a steal for doing this. If they could send out 50, and 25 of them could survive the round trip, and it would cost $600 million to do it. And we got 25 missions downloading 5 sets of observations each, 125 new asteroid study. That would be the steal of the century.
How do you feel about the resolution?
Love this idea.
Yeah, how do you feel about the resolution on this, Morgan? So they think they can go with this telescope within 1,000 kilometers. They'll get 100-meter resolution on these objects, and it would have an infrared spectrometer as well. So you would get...
Yeah, I think that's plenty to do this sort of gross survey that they want to do. And suppose that they, in fact, see 300 asteroids at 100-meter resolution. That's more than enough to identify the really interesting ones that we can then send more full-fledged missions to. You're not going to, this is not going to be a Dawn or a Rosetta-style observation of one of these objects, but we don't need that to realize, holy cow, this thing looks like an antelope or whatever the next asteroid's going to look like.
Right.
100 meters is more than enough for that.
Right. Or, that one's got a big platinum deposit, and that one has a ring, and that one is actually, 3 asteroids in a strangely stable 3-body orbit, etc.
Yeah, I love this idea, and I hope NASA won't touch this because it's too risky for sort of NASA style. But there are space agencies out there who are much more willing to experiment, and I would love to see one of them pick this up and try to make it happen in partnership with the Danes.
Paul, what do you think about this idea of an electric sail?
It's potentially interesting, and I mean, yeah, it's a viable way to have propellant and navigate around the solar system. I wonder if it would just end up being cheaper if instead of half of your CubeSat you had one of these giant tethers that you had to control. If you just had a little tail so you could like an antenna, and put in some communication gear and send it on a one-way trip and then just beam back the information, and then that's it.
I mean, one of the, with a solar sail, and people always ask, how can you raise and lower your orbit? And sort of the key with that is it's important to understand, how sort of orbits work, right? And that you're always going around the sun, and so you point the sail in one direction and you raise your orbit, and you point your sail in the other direction and you lower your orbit. And that's
how can a sailboat go against the wind?
Yeah, exactly. And so I think with this idea, you've got the sort of common center of mass with the tether, and then the thing rotates around it. And I guess that's how you're able to sort of change whether the direction of the thrust that you're sucking out of the sun's proton flow. But I mean, it's the kind of idea which I would love to just see implemented. And I think, as you said, Morgan, you get one of these built, and don't spend 20 million euro on one of them and tuck it in beside some SpaceX launch, and then let it complete this mission, and if it works, then send more.
Yeah, the larger idea here is the future of planetary science. I think everyone at all levels, NASA on down, is thinking about how do we use CubeSats to totally change how we're doing things. Because, we talk all the time on this show about how, okay, great, we've gone to Saturn. It could be 50 years before we go back. Or even you talk about Mars, we're going to Mars, every 5-ish years. And then you're doing one thing. The CubeSats have really changed how we study the Earth's environment, because you can throw 30 of them up there. And if 20 of them don't work, that's not great, but that means that you got 10 new ideas that you're trying out. And it doesn't have to be proven to work guaranteed. James Webb has gone through every conceivable test to ensure that it's going to work. And that's why it costs billions.
Yeah.
But if you're willing to try 20 great ideas and have only half of them work, then you're going to make all these discoveries that we weren't even thinking about, because we wrote that off as too technically challenging or too expensive to do. And it just like with SpaceX and other commercial spaceflight companies being willing to try things and fail, has given us reusable rockets. Being willing to try things and fail in planetary science and solar system exploration will give us new kinds of missions, new discoveries that we otherwise might have had to wait a century for.
But isn't it kind of the same thing with the breakthrough Starshot? Like they suggest this propulsion system.
Sorry.
They suggest this propulsion system to get a satellite that could travel to another star at at relativistic velocities. But wouldn't it just be wonderful to have a nano satellite make its way to Mars or to each of Jupiter's moons? Like that alone would be a tremendous boon to science. Far simpler, less work. And
I guess the question is, there's a certain trade-off of what is the scientific return for the money. So if, yes, you can build an incredibly small spacecraft, but then this proposed mission or design of a mission to the asteroids, if all it has is a very rudimentary telescope and an infrared spectrometer, and it can't even beam that data back to Earth, we have to wait for it to actually come back to Earth, and we have to go and pick it up. Otherwise, it'll just burn up in the atmosphere. And so even if it's down to $60 million, is that amount of information worth $60 million? Or is there some threshold where, no, you have to spend at least $500 million so you can do enough science so that the science per dollar is high enough?
Yeah, I think this is less about science per dollar for this mission or these observations. It's about taking your next $1 billion or your next $600 million and making them vastly more valuable. And so let's take another sort of different example. They're thinking about attaching a drone, like a helicopter, to the next Mars rover. And that's going to add a bunch of money. Let's say it's $100 million. I don't know. That $100 million, you're not going to get $100 million of good science out of that drone. It's just, it's going to have a really crummy little camera on it. It can fly for 3 minutes, and then it has to land and wait for it to recharge. But they think that by putting that little drone on Mars 2020, they'll be able to enable the big rover, the $2 billion machine, to travel 3 times faster over the surface of Mars, which means that in its 2-year nominal mission, it could go and see 3 times as many samples. You're not getting $100 million worth of science out of the Mars copter, but you're taking your $2 billion mission and basically making it like a $6 billion mission or 3 $2 billion missions. And that's how I see these works. Right. But that's a small gamble to make. And there's still going to have to be some threshold where you're reasonably sure that it's going to perform as intended.
I would say, yeah, I think that's a really good point. I would say in the world of infinite money, we would be trying to maximize science, and we would be trying to come up with novel engineering technical solutions so that in the future you can get even greater return. But in the world of limited money, is it worth it to, I don't know, like in the extreme case, sacrifice a generation of scientists so that we can spend all the money just on solving technical challenges so that not us, but our children or our grandchildren can do better science?
I mean, I don't really want to be sacrificed.
Yeah, like to Cthulhu.
Go on record here that I'd like to live and do science, but I think there's a balance to be found. If we, instead of sending a discovery mission every 3 years, we sent one every 4 years, And that means that basically once a decade, we could send out a swarm of these prototype CubeSats into the solar system to try new things. That's a trade-off that I'd be willing to make. Sometimes you're scouting new areas, sometimes you're trying new technology, but always with an eye towards improving your bigger bets. And I think finding that balance is what we're going to have to do. And different space agencies are going to balance that in different ways. And NASA might be sort of all in on the big stuff, and JAXA or ESA might be willing to go more 50-50.
Or in this case, the Finns.
You see that? Go ahead, Fraser.
Oh, I was going to say,
you see that in one of us is going to talk.
I'm letting you talk.
So the other agencies may step up. Unfortunately, we see this not just with NASA, but across astronomy and astrophysics for the past few decades, that funding in general has been going down decade after decade. And in the era of limited budgets, that introduces a certain conservative outlook where you're not willing, or funding agencies just aren't willing to make the risky bets, even if the risky bets have this great potential return on investment. They would rather see solid, demonstrable, incremental gains from using proven technology. We want to do what that previous mission did, but 20% more capable with 20% more money, rather than something crazy, because you can justify it to Congress. You can say, here's all that pieces of evidence that we know this is going to be a solid bet. And unfortunately, that looks like it'll be the outlook for the next, forever.
Yeah. Let's switch to your story, Dr. Paul Metzetter.
All right, stuff blowing up. Not as cool as Supernova. Well, actually, I feel like Nova, the traditional Nova or cataclysmic variable stars, I think they get short shrift. I think in some ways they're more interesting than Supernova, but everyone talks about Supernova. So I deliberately picked this story because I want to bring Nova back into the limelight. I think it's their time. I think it's their moment. 2017 is the year of the Nova. And this is an interesting analysis. There was usually Nova only happened once. We see a star flare up and then it returns back to normal a few days or a few months later, and then that's it. A very, very limited number of them will recur. And there's one in particular, V745 SCO, that flared in 1937, 1989, and then in 2014. And the most recent one in 2014, they were able to observe it with the Chandra X-ray Observatory and get some really, really, really juicy data on that. And based on the data, astronomers were able to perform simulations of what the initial explosion had to look like, at least in terms of geometry and shape, in order to produce those observations. And they found that this nova explosion, this thermonuclear detonation on the surface of a white dwarf, didn't happen in a perfect sphere. It wasn't a perfect ball. It was asymmetrical. And this is because they think there's a disk of cold gas surrounding that white dwarf that's swept up from the red giant star that orbits it. And this disk of cold gas prevented the shock wave from passing through it. Instead, it just heated up that gas, that disk, and then the disk glowed, but then the shock wave could come out the ends out of the top and bottom. And they produced this lovely image based on the simulations of what they think happened. I believe this image is 10 or 15 minutes into the explosion event itself.
And for the folks who are watching the live show, they get to see the actual image. Isn't it cool? For the folks listening on the podcast, we'll put a link in the show notes, but you've got to kind of imagine this this amazing sort of it's sort of like a flattened, like it's not this sort of perfectly spherical explosion that's coming off the thing. It's sort of got sort of one axis of the explosion and then another one kind of perpendicular to that, right? Like
right. So the disk is, so yeah, let's see if we can paint this mental picture for those listening. Let's say there's a pancake and that is the cold disk. And then on top is half of a broken egg. And that's the disk, or sorry, that's the material of the explosion itself, the shockwave coming up out of the plane of the disk. And there's one on the top, one at the bottom. So it's if you took an egg and then smushed it on the top and the bottom of a pancake.
Right.
There you go.
And then, but the middle of the egg was this kind of purple jam that you would like, injected into the middle of the egg.
Hot material. So that's the yolk. That's the yolk.
Yeah.
And then, what does a nova taste like?
A nova tastes like
burning.
And because it is high energy particles, it is X-rays and a little bit of gamma rays, so it is instant and immediate evaporation. But the core, the white dwarf, actually survives. So this isn't enough energy to actually completely detonate the white dwarf itself, which is why this can recur. Enough material piles on to the surface, goes thermonuclear, boom, and then wipes the slate clean, and then builds up material again, in this case over the course of 50 or 20 years or so, and then boom again.
And that's what makes nova much more dependable and interesting, right? Is that a nova will explode, and then where it happened, and then you can come back, you can observe the star then waiting for it to happen again, and then it can happen again, and you can get a sense of what's going on. While with supernova, the only time we find out about them is after they've exploded.
Yeah, a supernova may be spectacular, but it's a one-night stand. A nova is not as exciting, but at least you can depend on it.
Right, exactly.
This is a really great illustration of how astronomy in the 21st century is really different than astronomy in the 20th century. Because if we had made these observations, say, in 1960 or 1970, we'd be looking at this picture and trying to sort of work backwards to figure out what it implies. Today, with the help of really powerful computers, we can take this picture, then we can go back to sort of our basic physical models and generate 1,000 different scenarios and compare each one of those to the picture and say which one of these looks most like the picture we have. And it lets us sort of get back to the fundamentals of the situation rather than having to take the messiness of reality and try to walk backwards to understand how those initial building blocks must have been arranged.
Mm-hmm. Yeah. This is brute force science.
And it definitely plays back into this whole idea of transits that we talked about at the beginning of the show. So it's like a perfect circle. We've arrived back at our starting point.
It rhymes like a poem.
Well, let's wrap things up. Thanks, everyone, for watching today. You might be wondering where Kimberly was. She had a family event this week, so she'll be back with us next week. Don't worry.
We miss you, Kimberly.
We miss you, Kimberly. In fact,
she's done. And in 2 more weeks, there'll be only one person on this show.
Just be me. And we did have one more story, but I think we'll save that in case she wants to grab that next week, because it'll still be super. So there was a piece of exoplanet news. We were going to talk about it in sort of celebration of.
It's cool. Now you don't get to find out about it.
Now you don't know. You don't get to hear one thing about it until maybe next week, or maybe not if Kimberly chooses something else. Paul Metz-Sutter, where do people find out more?
They can find out more on pmsutter.com. That's my website. It has links to all the cool stuff I do, including the Weekly Space Hangout and my own podcast, Ask a Spaceman, my radio show, Space Radio, and all the stuff. There's like a whole page with a bunch of links. And if you're into stuff, you go to that page.
Okay, so let's say that I wanted to listen to your radio show.
Mm-hmm.
Where do I go to find out when that's happening? Because, I mean, you do this live show every week.
You got to move to Ohio. It's the only way.
You could call in, right?
Yeah, exactly. So spaceradioshow.com is the precise link to that. And we record every Thursday at 4 p.m. Eastern. We air on WCB Radio in Columbus. And coming up by the end of the week, as soon as I fill out all the forms and stuff, it will be a podcast. It will be its own podcast. So you can pull the stream later. But if you call up 888-581-0708, Thursdays at 4 p.m., you get to listen to me doing the show, and then we bring you into the show for a conversation.
That is awesome. Well, maybe I'll call in sometime.
You should call and ask like a really, really hard question.
No problem. That was one of my favorite episodes of Astronomy Cast that we did at DragonCon, where I just hit all of the panelists with the hardest questions that I had saved. I mostly stumped Pamela over the course of 10 years, and so I just hit the panel with every single one of those questions, and it was wonderful. Morgan, where do people find out more?
Well, I was bad and did not return to Twitter as so promised last week. So I'll just say, give us a review on iTunes, on Google Play, and of course, you can find my work at morganrenberg.com.
You literally just have to say I'm still alive on Twitter, and then my, then we'll know you're still there. But we appreciate you showing up here for the Weekly Space Hangout. And actually, I'm not going to Twitter shame you. I'm the worst. So, don't use Twitter. That's fine with me. But we talked about last week. Any interesting exhibits coming up in Fort Worth?
I've been thinking a lot about climate change in the aftermath of these hurricanes. And of course, the earthquakes, which aren't really climate change, but they show the tremendous devastation that our environment can wreak on our everyday lives. And so nothing new this week, but the gears are turning. And hopefully sooner rather than later, I'll be able to form these ideas into something that means something and has value in the world.
I mean, our thoughts go out to the poor people in Puerto Rico and the Caribbean that are just getting again struck by another
I saw
terrible
that the whole
hurricane.
island of Puerto Rico could be out of power for months.
Last I saw it was like 100%.
Unthinkable.
And of course,
unthinkable.
The Arecibo Observatory is on Puerto Rico. I don't know if anyone has been staying in touch with that. I don't know how the observatory is doing, but it's just been a terrible, terrible hurricane season. So, man.
On that down note.
Yeah, on that down note. Thanks everyone for listening. A big thanks as always.
Donate to the Red Cross.
Yeah, that's a good one. Actually, it's pretty great. If you search Google for the name of the hurricane, it will offer you links on how you can donate to contribute to the people that are being struck by the hurricane. So it's an easy way to sort of find out where you should contribute your money. Well, so big thanks to the folks from the WSH crew. That is who organized this week's guest, the Whoosh crew. Go to wshcrew.space if you want to join in that crew, and that's of course what provides this chat down here. We're still figuring out the new machine, how we work together as we move into this new season. But so far, everybody, I want to take a second and thank everybody for their patience as I constantly throw wrenches into their working process and jiggle everything up. Everyone's kind of used to it now, but that is just the way we operate, and I'm really glad everyone's sort of taking it quite well. So hopefully over the next couple of weeks we'll get smoother and smoother. All right. Thanks, everyone. Thanks, guys, for joining this week, and we'll see you all. I'm going to switch to the gallery view. Everyone can say goodbye. We'll see you all next week.